Namaskaram. In this session, we will discuss method of least square. Using this method, we can find a best solution if a system has no solution. This method is an elementary method for forecasting. Okay, suppose we have a data points like this. Here in x-axis, our variable is price, and here it is sale. We know sale depends price. Okay, so this data points means suppose price is here, then corresponding sale is here. Okay, that's idea. So naturally, if price is increasing, automatically sale is decreasing. That's why almost data points like this. Suppose there is a relation between these data points, or there is an underlying relation. Our aim is to find that underlying relation or approximate the underlying relation. Okay, so that is the idea. So how to find the underlying relationship for a given data? X1, Y1, X2, Y2, etc. X and Y. Here, this point is, you can take this point as our X1, Y1 like that. Okay, etc. up to the last point as X and Y. So we have n data points. So we have to find an underlying relationship between them for forecasting. Okay. Okay. So here we assume that the relationship is linear. That means actually all the points belong to a straight line. Suppose actually all the points are belong to straight line. But due to the errors in our collection of data, maybe points are not in the straight line. Right. Here it is clear that here the points are not in the straight line, but almost close to a straight line. Right. So that is our situation. We assume that underlying relation is linear. Okay, we have to find a best linear relationship between this data, but normally data is non-linear from because data are collected from our real situation. So normally they in that data involve some noises. Okay, so our aim is to find a best linear relation. So in this example, a best linear relationship means almost like this. Suppose we have an equation of the straight line, then you can easily forecast what is the value of the sale when the price is here. You can easily forecast the corresponding what is the corresponding sale. You identify the point on the straight line, then this is the corresponding sale. So this is easy. So once you have the relation, then you can easily predict. Okay, so to find this best straight line, first we are going to define residual. Residual is the difference between observed value and expected value. Observed value means actually observed from the real situation or our collected data. So in this case, corresponding to x1, what is our observed value? Observed value is y1. Okay, so corresponding to x1, our observed value is y1. So in this case, for example, O of x1 is y1. That is our observed from the real situation. This is our expected because we expect there is a underlying relation which is a straight line. Okay, so what is the expected value? Expected value is from the straight line. Okay, for example, suppose a data point is here. One second. Okay, because this point is almost close to the straight line. Suppose you consider this point. Okay, for this point, let be its coordinate is xi ya. You consider general point xi ya. Then what is the observed value at xi? So clearly this is our xi, right? So observed value is ya. Ya means this height. So this is our ya. Okay, what is the expected value of xi? Expected value of xi means that is from the straight line because we assume that there is underlying straight line relation. So that is from the straight line, the value of the straight line at this xi. So almost this one. So this is our expected value of xi. Okay, so you take the difference, the ya minus. So this difference is defined as residual. Clear? Observed value minus expected value. So next we are going to define a least square error. Suppose we have n data points like this x1, y1, x2, y2, x and yn. Then least square error is the sum of squares of residuals. So now we have there are so many residuals for example, for this particular point, this height is the residual. It is positive because ya minus this value. For example, you consider this point. In this point here, observed value is less than expected value, right? So here the difference is negative. So there are so many residuals like this. Some residuals are positive and some residuals are negative. Okay, so we are going to define least square error as the sum of squares of residuals. You take the square of all the residuals, then take the sum. Okay, by taking the square, you can eliminate the net effect of algebraic. Otherwise, the algebraic sum may be 0. Okay, that's why. So the least square error is equal to sigma I is equal to 1 to n e of xi whole square. Okay, so how to find this best straight line? So we can find this best straight line by minimizing this error. You got it? Because suppose there is no square, you simply take the sum. Then what happened? The problem is, suppose one point is here, one point is here. Then it is clear that it contains so many errors. If this error is 1, then this error is minus 1, like this. So the sum of this residual is equal to 0, but still there is an error. Okay, so to avoid such a problem, we take the square sum. We take the square then sum. Okay, then there is no problem of this sign. Okay, so anyway, to find this best straight line, our aim is to minimize this error. Or the best straight line, we can find the best straight line such a way that the corresponding E is minimum. Okay, for familiarizing the concepts, residuals and least square, we consider this problem. Find the residuals and least square error made in approximating the following data by a straight line y is equal to x plus 1.5. Okay, so first of all, we have to find the residuals. Okay, so first we are going to find the residuals. So we have to find residuals at each point. Okay, so our first data point is 0, 1. This is our x1, this is our y1, this is our x2, this is our y2, like that. Okay, we have only 1, 2, 3, 4, 5 data points. So what is E of 0? E of 0 is defined by O0 minus E1. What is O of 0? It is observed value at 1. Oh, sorry, this is O of 0 and this is E of 0. Observed value at 0. What is observed value at 0? That is 1. That is our data point, from our data point. Minus expected value of 0. Expected value from the straight line. Okay, we assume that there is a straight line relationship. So this is our expected straight line. So what is the value of the straight line when x equal to 0? When x equal to 0, this y is equal to 1.5. So our expected value is 1.5. Okay, so this difference is minus 0.5. Right. So this residual is negative. Similarly, you can find E of 1. What is E of 1? Observed value at 1. Observed value at 1 minus expected value at 1. What is observed value at 1? That is 5. Right. What is expected value at 1? That is from the straight line. That is 2 into 1 plus 1.5. Clear? So this is equal to 1.5. So this residual is positive. Similarly, you can find E of 2, that is 3 minus 5.5. This is from the straight line. Okay, 2 into 2 plus 1.5, that is 5.5. And similarly, you can find E of 3 and E of 4. Now these are the residuals. Now we have uh, 1, 2, 3, 4, 5 residuals. So now we are ready to find this least square error. How to find the least square error? You take the square of all these residues, then take the sum. That's all. So we know that our least square error is denoted by E. That is equal to E of 0 square plus up to E of 4 whole square. So this is the least square sum. After simplification, this becomes 11.5. So the least square error corresponding to this straight line for this given data equal to 11.25. Okay, so maybe this straight line may be best one. We don't know, but anyway, what is the best straight line for this data, or what is the best linear relationship for this data? That is a straight line of the form y is equal to mx plus v, which minimizes such error. Okay, suppose there exists a straight line such that error is equal to least square error is equal to some 3. Then it is clear that this straight line is better than this straight line for approximating this data. Okay, so our aim is to find the best one. Best one means error is minimum. Okay, so yes, error is 1.5. So next one, least square straight line. The least square straight line is the line that minimizes the least square error for a given data. Of course, that is the best straight line. That is the best possible straight line, or that is the best linear relationship between given data. Okay. So suppose this is our situation. We have data points x1, y1, x2, y2, etc. up to x and yn, and we also assume that there is a best straight line. So y is equal to mx plus p is the best straight line in this sense. That means this straight line minimizes the least square error for a given data. Our aim is to find this m and c because only this m and c are unknown. So our aim is to find this best m and c. Okay. So suppose y is equal to mx plus c is the best straight line in this sense for a given data. If data is linear, suppose these data points are linear, then it is clear that all the data points belongs to the straight line, right? If data is linear, then all the data points belongs to the straight line. That means data points satisfying this straight line equation. So that's why yi equal to mxi plus c. That means x1, y1 satisfies the straight line. So y1 is equal to mx1 plus c. Similarly, suppose a second data points also belongs to the straight line. Then y2 is equal to mx2 plus c. So etc. up to yn is equal to mxn plus c. This is possible only when data points are linear. Okay, we assume that the underlying relation is linear. That means data points are linear, but in from actual situation or from noise in our original data, data points are non-linear. That's a problem. Okay, so we have to find that linear relationship. So here we assume that suppose the points are belongs to straight line, then points satisfying this condition, right? Okay. Next, we are going to convert this system of equation in terms of matrices. Okay, so we can convert this system of equation a matrix equation like this. It is clear that if you expand this first row, this is mx1 plus c equal to y1, or first equation. Second one is x1 into m plus c equal to y2, the second equation. Okay, so this matrix equation represents this system of equations. Okay, so if data points are linear, then this system is consistent. That means there exists a solution m and c. But what is our situation? In our situation, it is clear that in most of the application, there is a noise in our data points. Okay, so it is clear that there is no solution for the system. Suppose points are not in the straight line. There is no solution m and c, right? So our aim is to find a best m and c for the system. Okay. Anyway, we know there are two type of metric system: inconsistent and inconsistent. If data points on the straight line, then system is consistent, otherwise inconsistent. Okay, in practical situations, our metric system is inconsistent due to the noise in the data points. So anyway, in general, suppose system AX equal to B is inconsistent. Okay, we assume that our system is inconsistent and we seek a least square solution. That means a best solution. So that is, we seek a vector x that minimizes the least square error. Okay, so we have to find a best x. Best x for the system ax equal to b. In our case, ax equal to means this is our system. Okay, in here, this matrix is a, this is our x and this is our b. Okay, so we have to find a best x, best m and c for finding this straight line, best straight line. Clear? Okay, the process of finding this best x involves inner products and projections. I leave the proof, but I just give the outline of the proof. Suppose we have a system like this ax equal to b, and we know that this system is inconsistent. And suppose this is the solution space of the system. Suppose this is the solution space of the system ax equal to b. Suppose this is a solution, this is a solution, all are solutions of the system. So our aim is to find a best straight line. Best solution of ax equal to b. Okay, so in terms of projection, actually here best straight line is this projection. Okay, we did not normally maybe x cap. So our aim is to find this solution x from the solution space of axb, which is closest to the system. Okay, and in terms of our error, you can view this distance as our error e. Okay, or suppose a solution is here, then is larger, bigger than this error. Okay, so this is the best one. Anyway, the underlying proof, its proof involves our projections and inner products. Okay. Anyway, I'm going to then okay, and this X cap is called least square solution of the system, this inconsistent system. Okay, this is the result, least square solution. Uh, Actually, this is a vector x is the least square solution to ax equal to b if and only if x is a solution to the normal equations a transpose ax is equal to a transpose b. Okay, you can find this solution by solving this system of equation. That's the idea. Okay, I leave the proof. A vector x is the least square solution to ax equal to b because here we assume that the system is inconsistent. It has no solution. Okay, then best solution is x. The best solution x is given by this formula by solving normal equations a transpose ax is equal to a transpose b. Okay, consider a problem. Find the least square straight line for the our same data 0, 1, 1, 5, 2, 3, 3, 6 and 4, 9. Okay. Okay, to find our best straight line, we have to find M and C, and we know that M and C satisfies this equation. If the relation is linear, then M and C satisfies this relation, and otherwise we can find the least square solution. Okay, so this is our capital A, this is our X, this is our B. So first of all, we have to form the system of equation corresponding to given data points. So in this case, what is our x1? X1 is 0 and 1. Here x2, 1, 2, 3, 4. These are our x values. All the second columns are 1. This is our A. Okay. Similarly, what is our B? B is given by yi's. So here 1, 5, 3, 6, 9. So this is our B. Now A and B is available. So this system is actually, this data points are not linear. So we have to find the best straight line. Then how to find the best straight line? By solving this normal equation. So next you have to find A transpose A and A transpose B, then solve. Okay, then you can easily find A transpose A. So here A transpose A is like this 30, 10, 10, 5. Also similarly you can find A transpose B. You take the transpose of A then into B, that gives a vector like 65, 24. Then we can make a system like this. So what about our normal equations? Normal equations are like this 30, 10, 10, 5. Instead of x means normally we have two unknowns. Normally we take m and c because first one is slope, second one is intercept. So that is equal to what is our A transpose B? A transpose B is 65, 24. This system is consistent. Okay, whatever be our system, suppose our system Ax equal to B, even though it is inconsistent, this normal system is always consistent. You can solve it. So by solving the system, we can find M and C. Here M equal to I think 1.7 and C equal to 1.4. Yes. So these are the solutions of the system. So now we are ready to write our best straight line for this data. Suppose this data points is like this, then the best straight line is given by the equation y is equal to mx plus c, that is 1.7x plus 1.4. So this straight line minimizes that least square error. You got it? So that's the idea of method of least square. Yes, this is a solution. And one more problem, find the least square solution to the system. Actually, this system is inconsistent. So you have to form the matrix equation of the system. Okay, what is the matrix equation of the system? Okay, this is the matrix representation of the system. So this is our A, this is our X, and this is our B. And this system is actually inconsistent. So we have to find the best solution. Okay, using our method of least square. So how to find the best solution? By solving the normal equations. A transpose Ax is equal to A transpose. Okay. So in this example, Now A is there. We can find A transpose A and A transpose B. So, this is our A transpose A and A transpose B. Now you have a system like this: A transpose A X is equal to A transpose B. This is consistent. You can solve the system using a Gauss elimination or any other method. Anyway, by solving the system, we have x, y, and z is like this. X is equal to 0.7597 and y is equal to 0.2607 and z is equal to minus 0.1772. Okay, so this is the best possible solution for the system in the sense of least square. Okay, okay, thank you.